Okay, let's go ahead and start off where we left off. There we go. So active transport, where we left off. So let's go ahead and finish up 5, get a good healthy start on 10. So active transport, right? So this is the uphill process. This is the one where you need energy in order to move. The most common one that we see is kind of what's called a direct transport. Let's sit here, sorry. Let's breathe on you guys too much. So the ATP one, the ATP driven one is the most common one. And that's kind of the one that we're going to be looking at for the most part. And so the important thing about all active transport is you're going from low to high, right? So it's an uphill process. That's the reason why you need energy to do it. And it typically uses carrier proteins. Now there's different types of carrier proteins that you run into depending on what they move and how they move it, right? So the first type of carrier protein that you run into is what's called a uniporter. And what a uniporter does is basically takes a molecule, one, and it moves it across the membrane, right? So that's one thing, uniporter. The other two are two different types of what's called multiporters, right? So the first one is what's called a symporter. And in a symporter, you're moving two molecules, but you're moving in the same direction, right? Sim means same. And so it's kind of like if you've got the little circular molecule going in one direction, then you also have the triangular molecule going in the same direction. So that would be an example of a symporter. And then you have an antiporter, which is moving two molecules, but they're moving them in the opposite direction. So in this particular case, you have your circular molecule that's going one direction, and you have your triangular molecule that's going in the opposite direction. So it's kind of like a northbound and a southbound lane on a 2-lane highway. And so each of these then are still responding to their concentration gradients. The difference is here, they're going against them, right? So if you notice in an antiporter, you're talking about building two concentration gradients at once, but those concentration gradients are pointing against each other, right? As opposed to with each other. And so this kind of gets that directionality idea of building concentration gradients. Now the poster boy for ATP driven active transport is a sodium potassium pump, which is an antiporter. And so what it does is it basically takes 3 sodiums and moves them out of the cell in exchange for 2 potassiums, which it moves into the cell. Where both of these are moving against their concentration gradient. So what you're doing is you're building a potassium concentration gradient where the high is inside and a sodium concentration gradient where the high is outside. Okay. Now, because you're both going uphill, obviously you need ATP, but the important thing about ATP is understand what ATP does. So what ATP does is it changes the conformation of the carrier itself. So conformation is just a fancy word for shape. And remember we said in chapter 4 that for protein, shape is everything. And that changing your shape is equivalent to function. Well, this is a perfect example. Changing your shape, your conformation, changes your function and allows you to be able to do your job. So let's take a look at the mechanism here. In step 1 of the sodium potassium pump mechanism, we have a carrier protein that is what we refer to as its native conformation. That's kind of its resting shape. Okay, and that's kind of where it is. Now, what are some features of this native conformation? Well, first of all, it has a couple of active sites in it. Right, little pockets where their substrates will bind. It's got active sites for sodium, 3 of them, right? That's these guys right here. And it's got active sites for potassium, 2 of them. Now, in this particular shape, the potassium active sites are inaccessible, but the sodium sites are available. You think of it sort of like in this particular shape, you've got like a set of chairs. The sodium chairs are nice, cushy, comfy chairs. Imagine like being on your feet all day at the mall, right? Which if you're not a shopper like me, it can be tiring quickly. And so you see that chair and all of a sudden it's like, whoa, that's so inviting, right? It's like you just want to sit down somewhere. and just take a load off. That's kind of what these sodium sites are like right now. They're nice and cushy and comfy. They're very inviting. The potassium chair is not so much, right? In this shape, it's kind of like, yeah, you see the seat there, but sticking up out of the seat is like a bunch of daggers. So you're probably not going to sit there, right? I mean, unless you're into sort of slicing up your backside, which if you are, don't tell me, because that's just something nobody needs to know about. But anyway, so that's kind of what the native conformation is. So the first step then is that the sodiums will go in and bind to their sites, and then you'll have the hydrolysis of ATP. So ATP will come in, hydrolyze into ADP and phosphate. And then what will happen is the carrier will hang on to this phosphate group. Now there's energy associated with this. And when it binds to the phosphate, the energy of that phosphate induces a shape change. And it changes it into its what's called its alternative or alternate conformation. Now notice it changes into this alternate shape in the presence of the phosphate. The phosphate is what allows it to do this. And so as it changes shape, the sites also change shape. So part of the shape change is now all of a sudden the sodium sites are no longer available, but the potassium sites open up. Imagine it like this. Your sodium, you're sitting down in your comfy seat. Then all of a sudden your seat starts to change shape underneath you. You start to feel the poke and slice of daggers starting to stick up into your backside. How long do you think it's going to take you to jump out of your seat? Not long at all, right? But at the same time, in the potassium seats, the daggers are retracting. And now all of a sudden, the potassium seats are looking pretty nice. But guess what? They're for potassium. So sodium can't sit there. So the only thing sodium has to do is to jump off of their seats and then to basically get dumped at the outside. Task number one completed. So then what happens after this? Now that your active site for potassium are nice and available, your potassiums will come in and sit down in their seats. And still your sodiums are unavailable. And then as soon as you lose your phosphate, you'll lose the energy necessary to maintain your alternate shape. What you do is you basically shape change again back to your native conformation. What does that mean? That means that the knives start coming up underneath potassium's chair. Potassium jumps out. That's exactly what they're doing here. And the knives retract in the sodium seats. So they're nice and cushy. So then we reset the system. So we're all back to square one. And we could do it again. So basically, when you take a look at the sodium potassium pump mechanism, it's just basically round after round after round of shape changes. So on one side, it binds to sodium. Then it gets the ATP infusion. So the phosphate will cause it to change its shape. And then it dumps the sodium on the other side, picks up the potassiums, loses the phosphate, changes its shape, dumps the potassiums, picks up the sodiums, adds the phosphate, changes shape, and then dumps the sodiums and adds the potassium. And over again, just back and forth and back and forth. Good. The potassiums are just going in there and sitting down. So they're not like sucking them in or wooing them in. They don't have to. It's an attractive place, right? It's just like at the mall, right? Like you don't have to be convinced to sit down in a nice cushy chair. I don't know if you've seen some of those massaging chairs, but they're kind of nice, right? So, you know, especially after a long day on your feet, you know, like when you get to that point where you don't really care, you're just going to sit down on the floor because you just want to get off of your feet. Yeah, you don't have to convince yourself to sit down in those chairs. It's just there, and it's like, yeah, I'm going to sit, right? It's kind of like that. Okay, what about the indirect? So the coupled transport. So ATP is involved in everything, right? But the difference is here in coupled transport, it's an indirect involvement. Most of your direct energy conversion is coming from the concentration gradient of another molecule. So for instance, in this particular case, in our example, we're using a sodium glucose symporter. So we're using the concentration gradient of sodium in order to power the movement of glucose. And this is kind of what it looks like. First of all, you need to build the concentration gradient, right? That's where ATP comes in. So you have your sodium potassium pump, which is building your sodium concentration gradient. Now within that concentration gradient, there's a lot of power. How do we know that? Well, we talked about Hoover Dam, didn't we? We talked about the conversion of energy to create electricity. That's exactly the same thing. It's the exact same set of physics. So basically you use that same energy conversion to basically transfer. So as sodium goes down its concentration gradient through the symporter, it transfers its energy and momentum to glucose, which allows glucose to be able to move as well. So here, basically, you're using your concentration gradient as an energy source to basically move your molecules. This is a pretty common sort of a technique that we see. However, I actually prefer describing this particular particular type of active transport more like with an antiporter, because it makes a little bit more sense. So imagine that we're an antiporter, and just kind of imagine it's a nice sunny day. It's going to be good in the 60s, right? So not quite hiking weather because the mountains are still snowing, but soon enough it'll be hiking weather. And imagine you got two people on the trail, one going down, one going up. The person coming down has a pretty easy job of it, right? Going down the mountain is pretty easy. Going up the mountain, yeah, a little tricky, right? So not so much. So with the mountain, with going down, imagine you got a 100-pound pack on your back. And as you're going down the mountain, it's actually like a controlled fall, isn't it? I mean, there's a lot of energy and momentum coming out of you, especially if you got a 100-pound pack on your back. I mean, literally what you're doing is you're just sticking your foot out there, right? And you're just kind of you're just breaking your fall, right? In small amounts, right? That's basically what you're doing as you're going downhill. So really you're letting your momentum basically just take over. So there's an incredible amount of energy coming off of you as you're going down that mountain. However, let's say somebody's coming up the mountain. Let's say I'm going to pick on Crystal because she's right there. I'm not going to try to get too close to her. Just kind of like, but let's imagine she's coming up the mountain again, also with a 100-pound pack frame. For her, it's a little slower, isn't it? Because she's like one step at a time and she's having to push and pull and drag herself up that mountain. So here's how this works. Here's how the energy transfer works. As I pass down her on the trail, I'm going to use like a martial arts move, right? Which is common in martial arts, where you use momentum and body center of gravity shifts in order to get your assailant off center so that they're easier to take down, right? That's the reason why some little itty bitty person can take down this big massive guy, right? Because it's not your mass versus his mass, it's his mass versus his mass. If you know how to get him off balance, he just falls down, right? He has no choice. What you're doing a lot of times in martial arts is you're transferring momentum, and you're using momentum in your favor and against the favor of your assailant. This is what's going to happen. So we already have a lot of momentum that's going on, right? I'm giving it out for free. I mean, as I go down that mountain, it's just going, right? There's a lot of energy in me. So imagine as I pass Crystal, what I do instead of just passing her and say, hi, enjoy the hike, right? What I do instead is as I go by her, I grab a hold of her and I transfer some of my momentum, martial arts style, into her. And I kind of push her up, give her a bit of a boost, like a slingshot up the hill, right? Well, for those next couple of steps, they're a little easier for her, aren't they? Because all of a sudden now she's not having to fight the load. She's got my momentum with her, giving her a bit of a boost. What I did was I transferred my energy going down to her so that she could use it going up. That's exactly what's happening here when you're talking about a concentration gradient. So I would be the concentration gradient molecule going down, shedding energy. And then as I shed it, I give it to you, which you take and you use it to power yourself up the hill. And if you imagine what this would look like, right, it would be like not just me passing by her, but imagine there was like a whole line of people like me right behind me, right, a whole line of us. And as every person went by her, they gave her a bit of a boost. Well, if you line up enough people by her to do that, she's going to have a pretty easy go of it, that mountain, isn't she? Right? So that's kind of what it's like. You have this kind of constant energy transfer. And that's coupled transport. So now what about bulk? Right? Bulk is a bit of a different creature. And it does take energy, that's true, but the energetics of it is a little bit different than active. It's the reason why we don't consider it active. It's also kind of got a slightly different set of parameters to it. For instance, with bulk transport, this is basically the movement of large macromolecules. Now remember, up to this point, what we've been doing is we've largely been moving small molecules, right? Small polar and non-polar molecules, little things like ions, like sodium and water, stuff like that, right? But now we're talking about big things, right? Big, massive macromolecules. So if you were to use the same strategy and poke a hole in your membrane to move these things, it would create a hole so big that it would basically risk the integrity of your membrane, and you could potentially do damage to your cell. So you got to come up with a different strategy. And we do, right? So we have mechanisms to move stuff into the cell and out of the cell. So endocytosis is moving stuff into the cell. And by the way, you've already seen bulk transport up to this point. We just didn't call it that when we got there. You've already seen endocytosis because we've already talked about phagocytosis. You've already seen exocytosis. So now we're just going to basically give it its proper name and then move on. Right, so for endocytosis, you have three different types. You have phago, pino, and receptor mediated. And this is basically the best way to understand it just by looking at pictures of it, right? So with phagocytosis, this is the engulfing of some sort of a food product where your cell essentially is going to pull in some, like in this case, a little bacteria. We're using a white blood cell here as our example. And it's going to pull in this little bacteria. And as it kind of progressively pulls it in, eventually these shoulders are going to touch and you're going to surround it with this membrane. And then, of course, you fuse it with lysosomes and you just basically chop the devil out of it, right? So this is a TEM of exactly what's going on, exactly like that. So you can see the membrane is already surrounding the bacterium, and eventually it's going to basically reach all the way around and you'll have engulfed it, right? So that's phagocytosis, that's cell eating. Pinocytosis is a similar process. The only difference here is instead of engulfing like a food particle or bacterium, what you're doing is you're taking like little sips, little samples of your extracellular matrix of the solution that's out there. Whatever solutes happen to be out there, you're just kind of taking them in. So it's more of a random sampling. Of your extracellular matrix, which makes a lot of sense, right? Because let's say that, you just need some extra amino acids. You don't really care where they come from. If there's a bunch of proteins floating around out there, just suck them in, and that'll give you a fresh batch of amino acids. So you don't really care what proteins are out there. It's all amino acid. Another thing that this will allow you to be able to do is sample your extracellular matrix, right? Because as a cell, you're the one who created that extracellular matrix, and it's your job to maintain it. So if you need to change that up, add something to the mix, remove something, you got a little bit more of this, a little less of this, then you need to know what's out there in the first place. So with this kind of a mechanism, it allows you to be able to sample what's in your extracellular matrix so you can adjust it and move it around a little bit. And so here you can see these little pinocytotic vesicles. They tend to be a little bit smaller, basically just kind of sucking little bits and pieces that are just right outside the cell. So this kind of keeps a constant traffic from outside the cell to inside the cell. Now, the newest one, the one that we haven't really done anything with yet, is receptor mediated. Now, this is an important one. Because it's going to be used to grab specific molecules. Yeah. So let's say that there's a whole gamish of stuff out there, but you're interested in just one molecule out there. You could care less about it. So what you want to do is you want to kind of reach out into your extracellular matrix. You want to sort of sort around through there. You want to search your matrix, sift around through it, find what you want, grab it, and then pull it in. Well, the only way you can do that is with a receptor protein. So you put some receptors out there, and they'll bind to your molecule. And then now you have to internalize it. But here's the problem. If what you do to internalize it is grab onto your receptor and just pull it in, that's not going to work. Because what's going to happen is it's not going to form a vesicle. It's just going to tear a hole through your membrane, right? It's just going to like rip through it. And that's going to damage your membrane. So what you have to have is a slightly different strategy. So what you do instead is, in order to avoid that, is you build a little foundation made out of a protein called plastic, and you embed your receptors into that foundation. So now you have basically these receptors embedded in your foundation, and you can grab onto this clathrin coat, and that'll actually pull the entire foundation. So you're not just ripping into the membrane. So you're just pulling on the foundation. The entire foundation will start to pull this vesicle downward until eventually you form your bubble, but you're going to create what's called a clathrin coated vesicle. And so these transmission electron micrographs, you can actually see this guy right here is one of those clathrin coated vesicles. The little blue halo is a colorized, it's a coloration. We added that, but that's highlighting and showing you where that little ring of clathrin is when we made this. And you can also see there's different vesicles in various stages of developing at the membrane itself. And then of course, exocytosis is easy, right? We've already seen that one. Remember we talked about the secretory pathway? We looked at the secretory vesicle with all that finished protein inside of it. Well, when that secretory vesicle floats out to the plasma membrane and fuses with it, it basically inverts, turns inside out, and then it dumps its contents to the outside world. That's exocytosis. It's a very simple process, just like fusing soap bubbles. This is probably one of my favorite electron micrographs of all, because you actually have caught a vesicle in the midst, in the act of exocytosis, of actually releasing. It's hard to do, because remember, when you prepare these slices for preparation for electron microscopy, it's all random. So you're just taking slices, and you don't know what you get. And you just have to prepare it and look at it, prepare it and look at it. And so it's very difficult to get this. Probably for this one image, there's probably at least several hundreds of images that didn't look so great. So it's really hard. It's a really rare one to get, because you're not just in exocytosis, but you're at the exact moment when it's actually spewing, ejecting all of its contents outside the cell. So here you can see it's already fused. It just barely fused, right? Because it's not very big yet. So it just barely fused. And now it's ejecting everything out. So that's exocytosis. For you table people, this is your table. So you can see you got your passive, your active transport, and your bulk transport. So for those of you who like to have everything on a nice, neat table, that's there for you. Okay, so chapter 10. So in chapter 10, right, I mean, we've been talking all semester long about how the ultimate goal of every organism is to do what? That's important. Yeah, right, to reproduce. But here we are, nearly completing the semester, right? Well, like a good 2/3 of the way through the semester. And we haven't talked about the holy grail of all biology, right? So it's like, you're probably thinking a lot of times students are like, well, wait a minute, reproduction is so important, and how come you haven't talked about it yet? This is it. So this is the first chapter that actually qualifies reproduction. Not for us, but if you're a single cell, cell division is reproduction. This is your first reproductive chapter. This is also an important chapter because it marks the beginning of a triad of chapters that go together well. So chapters 10, 11, and 12 work together as a triad, and they're all kind of interrelated. So chapter 10 is cell division and mitosis. Chapter 11 is meiosis and sexual reproduction. And chapter 12 is genetics. Probably the best chapter ever. Of course, I'm biased, but admittedly so. So how do they all fit together? Well, here's how it all fits together. Because when you're studying genetics, let's start backwards and move forward. Right? When you're studying genetics in chapter 12, one of the things we learned about genetics is the mechanism of genetics is meiosis. And so you have to understand the meiotic mechanism in order to be able to understand genetics well. So in order to understand genetics, you need to understand meiosis, which is chapter 11. In order to really wrap your head around meiosis, you need to understand cell division and mitosis well. So oftentimes these three go together. The better you feel about 10, the easier chapters 11 and 12 will be. Okay, so that's the reason why I always stress very strongly, work hard on chapter 10, make it feel good. Okay, it's like a pair of shoes, break those things in. If you have to soak them, right, and wear them wet so that they mold around your foot to make them feel comfortable. That's an old trick that actually Native Americans used to do a lot. Then do that, right? Because the better you feel and the better you know chapter 10, the easier chapter 11 will be. And the better you know chapter 11, the easier genetics will be. So let's go and let's just kind of sketch this out, because what I want to do is I want to kind of take a look a little bit more of like a global view, and then we'll zero in on 10 and focus. But what we want to do is we want to start off and see how all three of these things fit together, right? So we have mitosis, meiosis, and genetics. So ultimately, we all start at the beginning as a single cell. And in our cell, we have 46 chromosomes. We learned about that one, right? Didn't we, with the mitosis and chromosome squash one? So we have 46 chromosomes. So from the beginning, then, what we do is we essentially just do multiple rounds of cell division, where we divide, we create two identical daughter cells. But guess what? You're not done there, are you? Because you got a few more than two cells in your body. So let's keep going. So these guys will go through cell division. And now you have 4, but these guys will go through cell division. And these guys will go through cell division. And so forth. Get the idea? Until eventually you're born. If you're wondering what that is, it's like a little diaper. Right? So by the way, they don't come out with diapers. You actually have to get those for them, but I just added the diaper there. That's not actually part of the mitosis thing, so you don't get diapers by mitosis. That'd be cool. It'd be a lot cheaper. They're seriously expensive. Right, so this is basically your body. So what are you doing with mitosis? You're building the body. That's what you're doing with mitosis. Now, of course, you're continuing to build your body throughout your childhood. You're growing constantly. And then what you're going to do is you're going to take a subset of these cells, and they're going to go through a slightly different type of cell division, one that actually has 2 steps to it. And this is going to be meiosis, where you have a meiosis 1 and a meiosis 2. We'll talk about that in chapter 11. But the goal of this one is to produce 4 cells that are all genetically non-identical. So what do these become? These are our sex cells, right? So if you're a female, these are your eggs. If you're a male, these are your sperm. So then if you take one of these and add it to another individual, and you fuse these two together in a process called fertilization, then 23 plus 23 equals what? And back to the top we go. So what you see now is the interplay between mitosis, which builds your body from one cell to where you are now, trillions, right? And then meiosis, which basically builds the sex cells, eggs and sperm, so that you can actually create the next generation. Now, within that, notice that with any given sex cell, you're only choosing half of your genome. So only half of your traits get moved forward to the next generation. And so the passing then of those traits from you to your child, from one generation to the next, is genetics. So genetics is the study of the inheritance of traits across generations by utilizing a meiotic mechanism in order to create the gametes for those traits. But you need a functional mitotic body to live that long. And all of this takes what? Energy, right? So that's where your energy thing comes in. So it's not the ultimate goal, but it's definitely one of the first ones you have to solve. Yeah. But here you can see all three chapters interacting, right? So let's then take a look at the idea of cell division, right? So we're going to take a look at cell division. And there's a lot of parts to it, right? So for a single cell, for instance, if you go through cell division, it is reproduction. For you, it's reproduction. So essentially what's going to happen is you're going to go from one cell to two cells. So you have successfully reproduced. You're done. However, for multicellular, it's a little bit different. We can't just do cell division and say, haha, we just reproduced. It doesn't work that way, right? Because we got a lot more going on. So for us, cell division tends to be associated with growth. We just saw that, right? Going from one cell to a body of trillions of cells, that's growth. So mitosis is driving that. As you get older, when you stop growing, you're still doing mitosis. So when you damage tissue, when you cut yourself, when you break a bone, anything like that, you have to replace the tissue you damaged. So that requires mitosis. And this is just normal turnover. You have to always replace your cells as well, right? So the cells you have right now in your body were not the ones you were born with. Throughout the course of your life, you will turn over your cells many times. And that there's just a normal replacement process, and that requires an ongoing steady background of mitosis to replace those cells. So in prokaryotes, obviously cell division is very simple. And in eukaryotes, it's a little more tricky. So we'll start with prokaryotes, and then we'll talk a little bit about eukaryotes. So we'll start with our bacteria. So bacteria divide by a process called binary fission. It's a non-sexual or asexual life cycle, which basically means that they're clonal. So essentially, when you take a look at a bacterium, when it goes from one cell and divides into two cells, those two cells are identical. And those two will become four. Those four are identical. So they're all clones. So like a little bacterial deposit, like a little colony that you see on a petri dish, is actually a big pile of identical clones. Now, in cell division, there's a basic mantra that we have to always adhere to and keep to. And it basically goes in this order: duplicate, then separate. So why duplicate? Because you want to create two identical cells. The only way you can do that is by doubling everything and then halving it. If all you did was halve it, then what you would do is go from 46 to 23. That's not identical. So you have to double everything, and you have to separate those duplicates into two piles. So how do we start duplicating things? Well, we can always start with replication, right? The replication, which is doubling of your DNA. We have an entire chapter 14, that will cover replication, so we'll save the details for that. But one of the things you need for duplication of your DNA you need a start plate, right? So the thing about bacteria is the bacterial genome is circular. So if you take a look at a bacterium, that genome that's in the nucleoid region is actually a giant circle. It's just a kind of all folded and flopped on itself. Okay, we're not talking about those little itty bitty circular plasmids. We're talking about the main genome of bacteria. It's actually a big giant circle. So here's your replication enzymes. They come to this big giant circle and they're sitting there. Okay, wait, where do we start? I mean, do I just pick a place and go? I mean, is there a place to start? I mean, so how do I do this? Well, there is a place to start. We call it the origin of replication. This is like a start site. And then in bacteria, they also have a site of termination. So this is your stop site. So then basically what happens is you essentially start replicating at the origin. You stop when you hit the stop sign. And when you've done that, you've basically created 2 new chromosomes that then get sort of pushed to either end of the cell, and you just pinch the cell apart. And you got 2 new cells. Let's take a look at that process. So here's our origin of replication. Your enzymes are going to bind to this origin, and what's going to happen is they're going to roll in a circle. So one is going to roll counterclockwise, the other one's going to roll clockwise, and they're going to meet at the termination site. And so here you can see they're rolling opposite each other like that. And then once they roll all the way around, they run into the stop sign, and they stop. And this gets you to your magician's ring stage, where we're looking at connected rings. And you separate those rings, and now you have 2 separate identical genomes. And then you elongate the cell at this point. And you pinch it apart. You want to pinch it right about there. Okay, now how do you pinch it? Well, you pinch it by using a septum. Basically, this is like a protein wall. That forms a contractile ring, very much like a cinch cord. So it's like a little ring in that area, and it just you can tighten the cinch cord. It just basically shuts down like that. You do the same thing with this contractile ring. It'll basically cinch down like that, and as it does that, it's basically just pinch apart those 2 cells. And then once you do that, then you get these 2 different cells identical to each other, but now they're 2 individuals. So the septum is actually made of a specific protein called Phytse. And so Phytse is something we find in prokaryotes. And actually, when we take a look at a micrograph of it, here you can see this is your septum. So you can see this is a Phytse stain. So this is showing you the Phytse protein itself. And then when you kind of turn it to a slight angle, you can see it's not a wall. It's actually a ring. So this is your contractile ring. And so what happens then is it contracts radially, which basically means it cinches down, and then it'll pinch these 2 cells apart. And this is what you find in prokaryotes. But the question is, what about eukaryotes? So eukaryotes, they don't have Phytse. So how does a eukaryote do this? How does the eukaryote pinch it off? Well, even though a eukaryote doesn't have Phytse, what we noticed is that Phytse has a resemblance to something that we know about in eukaryotes. Phytse actually looks a lot like tubulin. And where do we get tubulin from? The production of microtubules, right? Now remember from chapter 4, we said that there's 2 big innovations in eukaryotes, right? One was the endomembrane system. The other one was a cytoskeleton, right? Bacteria do not have a cytoskeleton, so they don't have tubulin. So basically what you have is like an archaic protein that it looks like eukaryotes took and turned into tubulin. So how do eukaryotes pinch it apart? By using microtubules. So this is kind of really cool, right? To kind of see this kind of homology of structure and function, that these two very different cells, eukaryotes versus prokaryotes, have a common function that they need to do. And they basically come up with a similar solution. In this case, eukaryotes decided not to reinvent the wheel. They just didn't use FTSE. Now, why wouldn't you just hang on to FTSE, right? If FTSE is sufficient to pinch, why would a eukaryote actually like change it, right? I mean, why? It doesn't make any sense, right? What's the motivation there? Because if they're doing the same thing, then it doesn't make sense that you would just change it. So if you think about it from an evolutionary standpoint, right, here the evolutionary standpoint is that FTSE evolved into tubulin. But the pushback on that is, well, why would you need it to evolve into tubulin? If FTSE already is sufficient to pinch the cell apart, why change it, right? Don't fix it if it's not broken. So more than likely, I would argue an alternative hypothesis would be that even though they're structurally similar, they're not related. So FTSE didn't turn into tubulin. Eukaryotes invented tubulin on their own. They're structurally similar only because they're similar in function, not in ancestry. So basically, eukaryotes came up with tubulin on their own. That's something called convergent evolution, which is also one of the tricky parts about evolutionary studies that you always have to be on guard for. Because here's a situation where you can easily create a hypothesis that's compelling that FTSE evolved into tubulin, but it wouldn't be correct, right? Because of that convergence. This is the downfall of studying homology and morphology and functionology and things like that. This is the reason why genomics tends to sort of help a little bit more get kind of to the actual reality of how these are related to each other and whether or not they're related by descent or just by coincidence, basically. Christopher, you had a hand up. So they're similar in structure. I'm not quite sure what level of structure, but probably, you can have variation in structure, but sameness in structure. Like if I had you solve a problem and gave that to somebody else and they had no idea you were solving the problem, you would likely come up with very similar strategies to solve the problem. Not because you learned from that other person or that person learned from you. You had nothing to do with them. You were completely unrelated to them. You had no idea this other person existed. But you're similar in your approach purely because you had a similar solution to the function. You came up with a similar solution. So that's what's called convergent evolution. That's difficult to defend against, actually, because it's hard to detect, right, for certainty. Okay, so let's take a look then at a little bit about setting up our system. So we just talked about how things are going on in prokaryotes, right? So now what we want to do is we want to take a look at what's happening in other types of eukaryotes in particular. We want to deal with this nuclear envelope, right? Because this nuclear envelope is a problem, isn't it? Bacteria didn't have that problem because they don't have a nuclear envelope. We do, right? So the question is, how do we deal with the nuclear envelope? We got to get access to our DNA. But do you want to just break down your nuclear envelope? No, right? Because what is the most valuable, the most precious molecule in any living organism? Like if your house is burning down and you can grab one thing and run, this is it. What would that be for the cell? Yeah, the nucleus, right? Which is the DNA, right? Because your DNA is your plan for you. If you don't have your DNA, you are functionally non-existent, right? So this is that one thing that you grab, so you have to protect it at all costs, right? Is that another question going up? Okay, so here's the thing then. So we have different strategies to deal with access versus protection. So let's take a look at some protists here. So these are the plant-like protists. So what plant-like protists, you remember plants don't have a centriole, right? So they have a different type of a microtubule organizing center. So we don't know what that is. But here you can see this sort of other microtubule organizing center will organize microtubules. You'll build some thoroughfare microtubules that will basically go all the way through from pole to pole or from center to center. And then you have some lateral microtubules, which will basically kind of reach in and sort of grab onto the chromosomes and move them. Okay. But notice what you don't do. Your nuclear envelope remains intact. Okay. So animal-like protists will have a similar situation. Well, they've got centrioles. So they'll around their centrioles, they'll still build their thoroughfare microtubules that connect pole to pole. And they'll have microtubules that penetrate into the nuclear envelope and grab onto the chromosomes and pull them. Again, though, notice your nuclear envelope is intact. How do yeast do it? A different kingdom, right? This is kingdom Protista now. Yeast goes into kingdom fungi. So how do they do it? Well, what they do is they actually build what's called a spindle pole body on the inside of the nuclear envelope. And from there, they build a fair amount of microtubules. See a pattern going on here that connects pole to pole, and then lateral microtubules that grabs onto each of the chromosomes and poles. But it's all inside the nuclear envelope. So the nuclear envelope remains intact. So why would you want to leave your nuclear envelope intact if you're these guys? What's life like for you if you're a protist? Imagine you're a euglena. You're one of the plant-like ones. You're floating around in this big giant pond. Yeah, everything wants to do what to you? Yeah, everything wants to eat you, kill you, right? So you have all this negative stuff going on. It's a very dangerous environment, right? And that's before you start to get to crazy, wacky weather patterns, right? Where it's like freezing in the morning and 66 in the afternoon. Hello, I'm looking at you today, right? So like, you know, where basically the little pond you're swimming in could be frozen and then a couple of hours, nice and hot. And that's before you get to all that. So what's in a dangerous environment like that, what's the last thing you want to do? Yeah, so you don't want to expose, right, yourself, because why are you keeping your nuclear envelope intact? Yeah, what happens if you didn't have it intact and you're out there in this dangerous pond? Yeah, the most precious thing you have in yourself is vulnerable to attack, right? And that's a bad thing. So cells in general, especially eukaryotes, do not want to drop their nuclear envelope. Because for them, dropping the nuclear envelope is like dropping your pants in public. You like where this is going already, right? You're like, yeah, another one. Think about it. You got to go. Right. And it's to the point where it's like, okay, this is not going to go well. Because I'm in the middle of a big crowd of people. There's nowhere to go. Right. There's no bathrooms. There's nothing. And you're in the middle of a big crowd of people. So this is really going to go one of two ways. And it's not going to go well for you. Right. There's going to be stories after this, one way or the other. The question is, how do you want them to go? Not really, right? But think about this. You're out in public, right? And you're like, okay, I got to do this. I mean, are you going to drop your pants out there? Why not? Yes, you'll be arrested. But think about it this way. I didn't tell you what kind of people the crowd is, are in the crowd. Some of these people in the crowd could be your enemies. If there's a bunch of people who are your enemies, a crowd of people who are your enemies, are you going to be interested in dropping your pants right at that point? There's a common thing that a lot of people don't know about football players. It's actually more common for a football player to pee their pants than you realize. Ask any football player. Yeah, because during the game, they're hydrating, so they're drinking a lot. But there are no porta potties on the side. Take a look on the sidelines. There's no porta potties. There's nowhere for them to go unless they go to halftime. So imagine you've got some big old hulking offensive lineman who's out there on the football field and they've got to go. What do you think they're going to do? There's many actually football players where they've actually had stories of like who's Schlereth, Mark Schlereth, right? The famous, is he Hall of Fame now? I think, yeah. So great offensive lineman. I was a Raider fan. I had lots of respect for Schlereth. I loved his style. Him and Tommy Nalen, those guys were just awesome. That was an awesome offensive line. That was one of the best back in those days. It was fronting Elway. But he actually has a story where he was like, he was just laughing because, he was all like, yeah, all the fans up there don't know that I'm pissing my pants right now. Yeah, he just looked right there on the field. He's like, okay, let's go. Because like you can't tell if it's sweat or if it's pee. Yeah, so it's like, it happens quite commonly. But I mean, here's the thing, right? Here you are out there, Mile High Stadium, full, right? All your fans. Are you going to drop your pants at that point to do your business? No, because it puts you in too vulnerable a state, doesn't it? You're just going to do your business, however it needs to be done. You're going to move on. So, little known fact, the ugly, unmentionable side of football. Yeah. And there was another story, was like a linebacker. Who was it? Greg, not Hardy, the blonde guy. He used to play for the Panthers, like not Kuechly, before Kuechly. It was the Jaguars maybe. It was like before. That's like when they first came in as an expansion team. But he basically was saying that like he would have like his teammates stand in front of him to block the cameras, and he would just take a towel and just pee in the towel. So while they were blocking him. So like a lot of times when you see them on the sidelines and they kind of got their coats out like that and they're kind of blocking them, a lot of people, they're like, oh, they must be like talking some crazy football strategy that's super top secret. No, probably there's somebody back there who just needs to pee and they're just trying to block the cameras because the cameras are all over the place. So is that well, I don't know, because I don't think those stories have changed in the recent. I mean, Schlereth wasn't that long ago. You'd think it'd be a little kind of cruel and unusual, right? It's like at least give him something to like a urinal or something like that, just to. Yeah, it's like, yeah, I don't know. Yeah, I mean, you would think, but oh well. I guess that's all part of the manliness of football, right? It's like. Yeah, no, right. Yeah. Yeah, just do what you got to do. Yeah. So, by the way, if you're wondering, by extension, battle can also be similar sort of a thing, right? I mean, if you're like in a trench and you're fighting, you don't really care at that point. It's like, I don't really care about etiquette, about peeing somewhere, a latrine. It's like if I'm in the midst of battle and I'm being shot at and I got to go, guess what? I'm just going to go in my pants and I'm just going to keep, because there's bigger fish to fry at that point, right? Staying alive and not getting a bullet in your head is a little bit more important than whether or not you should stop and pee in your pants or not, right? I mean, what? It depends if it's really cold, yeah. But honestly, you've got a better chance with hypothermia than if you're in the middle of a battlefield with bullets whizzing around your head. You can deal with hypothermia after the fact. Yeah. So then what do? Animals, what we do is we break down the nuclear envelope. But why? Why can we get away with that? It's simple. We're multicellular. So our cells aren't out there in a dangerous pond. They're deep in our body, protected and safe. So it's kind of like going into a restroom where you're locked into the stall and you're safe. There, it's not a problem. You can drop your pants because it's a safe area for you to be able to do that. So let's take a look at our chromosomes. So basically, we already know that humans have 46 chromosomes. We learned about that one with the chromosome squash lab. We have 23 unique pairs. Correct. Yep. We'll get to all those, the features of each of those phases. So we had 23 unique pairs for a total of 46. Now, in general, having extra chromosomes is a bad thing, right? So a lot of you guys had extra 13 when you did your chromosome squashes, or an extra 18, or an extra 21, or an extra X, or an XO, which is a Turner syndrome. But typically speaking, the autosomes, which are numbers 1 through 22, you typically have 2 of those. So yeah, that gives you up to 44. And you got 2 sex chromosomes. So that gets you up to 46. The autosomes are invariable, right? So if you miss an autosome, that's pretty lethal, it's pretty catastrophic. And so actually, even though we had that big list of, potential things, if you actually looked at the laundry list of the problems that a newborn with Patau's or Edwards has, it's clearly, wow, this is a train wreck. This is not going to go well. The only real viable trisome where you have an extra chromosome that we ever really know about is Down syndrome. But what a lot of people don't realize is that a Down syndrome person doesn't have a full life. Their life expectancy is maybe in their 50s. So they don't live very long at all. So having extra DNA or missing DNA is, for us, for mammals, is catastrophically lethal. That's not true for all organisms. Plants, they can actually accommodate more DNA, more chromosomes, even entirely sets of chromosomes. They have a lot of flexibility in them. Oh, sure, that's true. We actually do that a lot. Matter of fact, that's actually the basis of a lot of our agri-industry. So most of what you buy, like at a store, has been modified. Not GMO, just like modified in general. So if you just take a look at GMO as a genetically modified organism, that pretty much and use that as your blanket, that pretty much accommodates everything you're going to pick up in the produce section, everything, whether it says non-GMO or not. I know that. I know that by one simple question. How many of you guys like strawberries? It's okay. You're going to love strawberries. I love them, right? For me personally, the best fusion is like strawberries and bananas. It's like perfect, right? That's like the perfect combination. A close second is maybe mango and pineapple or something like that. That's a pretty good one too. I love pineapple. Mango's also pretty good. But I've got a soft spot for the classics. But when you go to the store, what kind of a strawberry do you look for? The ripe ones, which means what? Bright red, and do you get the little itty bitty one? You get the little itty bitty one? No. You want to get that big, fat, right? The biggest, fattest, juiciest strawberry you can find that is like bright scarlet red, right? That's the keeper, right? Okay. Now that you know what a strawberry looks like at King Supers, do you know what a strawberry looks like in the wild? Yeah, they're little. I mean, a big strawberry would be maybe the size of my pinky nail. Yeah, well, even then, like an actual wild strawberry is not even edible. They're so tiny. Yeah, they're not quite as red. Yeah, they're not quite as red. Yeah, and they're really tiny. I mean, you literally like walk through a little patch of them and not even realize what you're walking through until you look closely. It's like, wait a minute, something looks familiar about that. And you look closely, it's like this itty bitty bitty strawberry on there. It's like, that's not like a little itty bitty strawberry. That's because they're wild type. That's like what a wild strawberry looks like. I mean, you can eat them, but I mean, there's not a lot there. Yeah, but the problem is everything we eat is selectively bred. Yeah. Everything. It's genetically modified. So in breeding plants and during domestication is genetic modification. So that's the reason why when you take a look at that, what you actually see in the grocery store is actually a strawberry plant that is not, that has like 8 sets of chromosomes. So we bred extra sets of chromosomes into it. And as it turns out, this gets to your question, right? As it turns out, the more sets we add into that, the bigger it gets, which is the reason why we get these big old giant strawberries. Here's another evidence of one. How about this one? How many of you guys love bananas? Yeah, right? Yeah. So bananas, all fruit, are the seed-bearing structure of the plant. But you don't see any seeds in bananas, do you? But in wild bananas, there's seeds, right? So that tells you a little, so we're kind of messing with the fruit. So most everything we actually buy has been modified. Even our wheat is not wild wheat. Nothing we consume or buy is native. We have, through agriculture and breeding, we have turned them into hybrids and things like that that are specifically designed for our purposes. So it's genetic modification. Well, that's my question. Yeah, when I hear people get kind of all a little crazy about GMO, I kind of raise my eyebrow, especially at the grocery store. It's hilarious, right? I'll see somebody who's like snickering and you know, talking about, oh, that's been genetically modified. And then they pick up this big basket of gigantic strawberries. And I'm like, so you just are crapping on this one over here, but you just basically picked up a genetically modified fruit and you don't have a problem with that one. So there's a lot of hypocrisy, honestly, in the GMO cause. And a lot of, and that's kind of, you know, I kind of raise my eyebrows a little bit because first of all, a pro-GMO person or an anti-GMO person has actually never intellectually sat down and delineated what is good and what is bad. Like, what is the list of good? What's acceptable? Where is that line? What's unacceptable? So there's no reason or logic at all. It's basically all heat and no brain a lot of times. And when you add that in there, typically you get a lot of hypocrisy. And that's what I see. I actually see it in the shoppers. You know, they're making big deals about all this and they're crapping on all this, but it's like, you just basically went from the fire to the frying pan. That's because you're thinking from heat, emotion, and not actually using your brain instead. So that's kind of like the hysteria effect. Now, I'm not saying that it doesn't need to be considered, right? But not everything is dangerous. Well, I mean, vegans do have nutritional deficiencies. I don't know that they need to kill a bunch of animals to solve that problem. I mean, they usually can take like an amino acid shake or something like that to supplement. That would usually do the trick, I would think. I don't think they have to kill anything if they don't want to. But yeah, they do have deficiencies that they have to be aware of. Iron deficiency is a big one, actually. They have to always take iron supplements. Yeah. So, okay. So let's take a look at our DNA structure, right? So when you take a look at DNA, we kind of talked a little bit about this before. We're just going to revisit this and sort of expand on it a little bit. So when you take a look at the complex of DNA, remember we talked a little bit about DNA sort of being a complex with these proteins, these little histone drums, right? These proteins called histones, which form these complexes. And then you wrap your DNA around them. And so this is kind of like your basic chromatin style. Now, when you take a look at this basic chromatin in a non-dividing cells, there's different looks to this. So there's a little bit of dynamicness associated with the structure called chromatin structure. So, and we have two different types of this. So we have what's called heterochromatin, which is an unexpressed type of chromatin. Now, the reason why it's unexpressed is because this is a highly condensed and tightly packed chromatin. And the reason why it's not expressed is because the genes are inaccessible. So what you've done is you've taken this little chromatin line and you can pack it together even tighter and tighter and tighter. And when you pack it together tighter, you're basically making the DNA that's wound in there inaccessible. That's the reason why it's not expressed. We call it transcriptionally dark area. So if you have a gene in the heterochromatic region, then you're not going to get activity from that gene. It's a way to silence the gene. Now, alternatively, however, you've got a region of euchromatin. So this is a looser region. Where the genes are accessible. So you kind of loosen it up a little bit. And so you get expression of these genes, so activation of these genes. As a matter of fact, this whole process, this whole kind of just packing the DNA tighter versus looser, loosening it all up, there's a lot of dynamic activity here. So you can really make your chromatin structure very loose and accessible. You get a lot of gene activity there. Or you can basically do various degrees of packing it all together and condensing it down, which is various degrees of silencing. So what we've noticed in research the last 20 or so years is that one way to control how a gene is turned on or off isn't by having some sort of regulatory protein that turns it on or off. In some cases, for some genes, it's a simple matter of just rechanging the chromatin structure. So one way to silence the gene is to just condense that structure, and it basically silences the gene because you don't have access to it. So that is chromatin. And of course, each one of those little individual histone drums, the DNA wrapped around it, is what's called a nucleosome. And the way that this is actually arranged, the way the DNA actually wraps around it, is simply an electrostatic attraction. So the proteins in the drums, histones, are positively charged. DNA, because of the phosphates, is negatively charged. So you have that natural positive negative interaction between the protein and the DNA. That's kind of what zippers the DNA onto the protein itself. But remember we said before, the electrostatic attractions are weak, right? So why wouldn't you want to take your DNA and covalently link it to the histone? That'd be very strong, wouldn't it? Would that be very accessible? No, right? Because remember, DNA is not a dusty old book that you stick in a library and you never refer to. It's a working document. You're constantly accessing it all the time. It's like a cookbook. It's like a good, dirty cookbook, right? One where it's like you use this recipe so much. I mean, it's got stains and stuff all over it, right? You're kind of like wiping it. It got a little windshield wiper thing going on to kind of clean it off so you can like always constantly use it and things like that. So this is an active document. So you need access to it, but you also need to protect it. So you've got these two opposed things. I need to protect my DNA, but that eliminates access. I need to access my DNA, but that eliminates protection. So this gives you a balance between the two. So I can wrap it securely around these systems for protection, but because it's a weak force, I can easily unwrap it and get access when I need it. So that's basically what holds DNA together. So here's your DNA molecule. So here's your naked molecule, and then this is your nucleosome. You see your DNA is wrapped around it twice, and you kind of pin it with another histone there to kind of keep it from unraveling. So this is kind of like your double helix to your chromatin. So as we start to move up into structure, like what's the next level of structure after this? So if we have these little nucleosomes, then what's the next level of structure? Well, the next level of structure is what's called the 30 nanometer fiber, or the solenoid. This is basically a cylinder of chromatin. And it's typically, you'll find this in a non-dividing cell. So you're not ready to do cell division just yet. And you can basically kind of go back and forth between this state and your other two states, right? So ultimately, when you take a look at your solenoid, this is what it looks like. So here you can see your little chromatin string, basically just being kind of wound around in this sort of long cylindrical type of solenoid. And the diameter here is 30 nanometers. That's why they call it the 30 nanometer fiber. So basically then when you look at the whole chromatin dynamics thing, this is a very dynamic process. So in a normal non-dividing cell, you can always go back and forth between your 30 nanometer fiber to a more condensed heterochromatic region. You can unwind your 30 nanometer fiber to get more access to it. That's going to be more like a euchromatic thing. And so you kind of have these constant sort of dynamic changes in chromatin, depending on whether or not you need to get access to those genes in order to read them. So that's all normal. This is all non-dividing. But what about if you're dividing, right? So for a dividing cell, you have to compact things even more. It's a process called chromosome condensation. So think about it this way. Imagine your DNA is like a fine china set. And let's say you're an East Coast family. You've been on the East Coast for like generations, right? So there's like a long history of your family on the East Coast. And you got this family china collection that's been added to from one generation to the next, and it's old and antique and priceless and irreplaceable. And what you want to do is you want to move to LA. How do you move your china set? You just grab a plate and go. Box it. Do you actually ship it though? Yeah, you drive it, right? Think about it. So what you do is you take your china set and you carefully separate it out, right? You take all the plates, you put them together. Do you put plate on plate? No, you put a little padding in between the plates, right? And then, so there's no clink on clink, right? And then you put it in a box, and then you fill in any holes or gaps in between there with even more packing, maybe bubbles or popcorn or whatever. And then you make sure there's nothing in there that's moving at all, not even an inch, right? And then you tape the box up, and you do the same thing for the cups and same thing for the saucers and whatever else, right? But then you tape up this box, you write fragile on it, and you write good things like, break this and I will come and kill you and your children and your children's children's to 10 generations. Sounds pretty extreme. But think about it. You're talking about a priceless china collection. Something breaks there, it's not coming back. You can't replace it, right? It's a big deal. So here's the shipping thing. So do you just hand this over to UPS and say, here, take it to LA? Not if you're in this family. I don't know what it's like to be in one of these like highfalutin East Coast families with something like this in it. I mean, I've always been a bit more of a gutter blood myself, a little bit more of a stray dog in nature than a AKC winner. That's just me. Right. But more than likely, what are you going to do with that box? Yeah, you're going to be like, you know, this box, this one here, I'm going to tuck this one under my arm, and where I go, it goes, right? So I'm going to put it in the passenger seat next to me. I'm going to put the little seat belt on it, right? And when I sleep in the hotel, it's going to have its own little spot. I'm going to pull the covers up over it. I'm going to sing to it a little lullaby, maybe give it a little bit of bedtime story, right? Call it Wilson if you're into the movie Castaway. Right, maybe it's not quite that bad. It depends. Well, I don't know. Sometimes moving can affect your mental health enough to where you would probably treat your box better than that. But you're taking care of that one, aren't you? So you move it all to LA, and then what do? What's the first thing you do once you move to LA? You pull out the couch, the bed? No, more than likely what you're doing, you find the china hutch, right? All the display cases. You pull out all that china and you get it all up on display. What did you do? What you did at the beginning was you condensed your collection into a safe, structural, movable package. You moved it, and then you decondensed it and you opened it back up and put it back on display. The exact same things happen to your chromosomes. So when you get ready to divide or move your chromosomes, then you have to condense this down into a movable package. You start with your solenoid. So from your solenoid, what you're going to do is you're going to take these little cap-like scaffold proteins and you're going to cap the ends of a solenoid and create what's called the hairpin loop. And then you're going to take a hairpin loop and you're going to basically take a shaft-like rod of a scaffold protein and you're going to basically insert the hairpin into that rod. Multiple loops will go into that rod. And then eventually what you'll create is what's called a rosette. Now, if I were to take a look at this structure side on, I would see this little rod-like structural protein, but then I'd see the edge of the rosette. Different rosettes will have different sizes to them. Some will be big. Some will be a little bit smaller. But you kind of stack them all right next to each other. And then eventually what it starts to look like is the dividing chromosome, the cheese puff chromosome, the cheetosome, right? That little puffy chromosome that's now ready to move. This is your China collection, all padded up, all taped up, and it's ready to move. So that's basically what you do. Your karyotype, you've already seen your karyotype, right? Because you guys did that with your chromosome squash during lab. The best way to take a look and see what kinds of chromosome numbers you have. Also the best way to see the nature of our what's called ploidy. So ploid refers to chromosomes. And we are diploid, diploid, two. That means we have two sets of each chromosome. We call that 2M, where M is equal to the number of chromosomes in the genome, right? So we have 23 unique chromosomes. We have 2 of each. That gets us up to 46. So our haploid number is then the N, right? This basically means you have one set of chromosomes. This is also the same as the number of chromosomes in your genome. And for us, that's going to be 23 because we have half the diploid number. By the way, the gigantic strawberries that you buy at the store that are big and juicy are not diploids. They're actually octoploids. So they got 8 sets of everything. That's what we bred into them. We bred in extra sets of their genome. That's what makes them bigger. The wild strawberries are diploids. The bananas with the seeds in the wild are diploids. The ones we get at the store without the seeds are tetraploids. So most of what you get has actually been agriculturally and genomically modified from what it actually is in the wild. So when we have this diploid relationship, then we have, and we saw this with our karyotyping, right? So we saw this with our chromosome squash. We've got 2 of every chromosome. What that means is each of these pairs is what's referred to as a homolog. So they're homologous, which basically means they're the same, but different. So think about that, right? What does that mean? I mean, how can you be same and different at the same time, right? That's like an oxymoron. Well, here's what it means. Well, if you take a look at mom one versus dad one, they're the same in the sense that they have the same gene. Let's say, for instance, hair color. But let's say dad has black hair and mom has really light blonde hair. So what you have is dad's black version of the gene for hair color and mom's light version of the gene for hair color. So even though they have the same gene, hair color, they have different forms. So they're homologous. They have the same genes, but they're different versions of those genes. So we know our mantra, right? So we know that our mantra is duplicate, then separate. So we're going to talk about replication. We're going to talk about it in detail, however, when we get to chapter 14. But normally when you first start off, you have your two homologs. So this is like mom one, this is dad one. So before replication, you basically have two chromosomes and you have them a centromere, which is like a little constriction point of the chromosome itself. Then when you go through the duplication, right, which is going to be your replication, what's going to happen is you're going to basically create two copies that are attached at the centromere of mom and two copies attached to the centromere of dad. So each one of these is referred to as a sister chromatid. So you have 1, 2, 3, 4 sister chromatids. Each one of those is a copy of chromosome 1. 2 of mom attached to the centromere, 2 of dad attached to the centromere. This is what it looks like. So let's say this is dad 1, this is mom 1 before replication. Once you go through replication, then you're going to create your 4 sisters, 1, 2, 3, 4. So the 2 dads are connected together at the centromere. And the sisters are held together by a protein called cohesin. This is like a protein glue. That holds the sisters together. So now what's happened is you've doubled everything, right? So you've gone from, in this particular case, 46. Now how many do you have? Now you've got 92, right? So replication doubles everything. So you've gone from 46 chromosomes now to 92. Okay. And then when you separate them apart, you'll go back down to 46. And that's how you stay at 46. So we talked a little bit about replication. We talked a little bit about division and duplication. But remember, all these activities that are going on are all happening within the context of a whole cycle for the cell, called the cell cycle. This is like the life cycle of the cell. There's 5 main phases of this life cycle. So it's just like, you know, if I wanted to study you and understand you better in this particular phase of your life, the best thing for me to do is to kind of get a broader context, right? Of like, what does your life cycle look like in general? So if I wanted to understand somebody at a particular life stage, then what I want to do is understand all the life cycles first, right? So I do understand your newborn life cycle, going through childhood, the whole growth phase, your teenage stage, your young adult stage, your middle age stage, your older stage, right? So understand all the parameters of what each one of those stopping points are like for you in your life cycle, so that I can better have a context and perspective for understanding how your life is right now, right? And that's kind of what we do. We want to understand what the cell is doing by understanding its overall life cycle. And it's divided up into 5 phases. Just like us with our own life cycle, it all begins with birth, right? So at first we're born, and then we enter childhood. The cells basically also enter a cellular childhood as well. That's called G1 or gap 1. It's a pause in the cycle. In G1, this is your primary growth phase. So this is basically where the cell is growing and getting to its adult size, if you will, right? Now, this typically will take some time for most cells, and so they're kind of taking their time with this one. That's the reason why there's a bit of a pause in the cell cycle, because it's busy growing up. But eventually what's going to happen is the cell comes to what's called a restriction point. It's a decision time. So after it becomes mature in size, mature in body, if you will, it has to make a decision, and it has to answer a question. The question is, do I divide? And there's only really two answers to this. It's either yes or it's no, right? By the way, the same thing happens to us, doesn't it? We grow up, our bodies become mature, and we have a similar question answer. Only what's our question? Yeah, do we have kids, right? And that's a yes or no question. There's no deferral to that question, right? To not answer the question is to have the question answered for you. There's only yes and there's only no. Now, the important thing is, if you divide and you say yes, then you commit to the cell cycle. If you say no, then you commit to a functional state called G0. Same thing's true for us, right? There's a sense of commitment with the idea of having kids. So if you say yes to having kids, it's like it changes your identity. Good. It's like a side. Yeah, it's like a parking lot on the side. It's not technically part of the 5. So, right. So if you have kids and you say, I'm going to have kids, when you have kids, that changes your identity, right? I mean, if you talk to a parent, it's like they always identify as a parent. It doesn't matter what happens to their kids. They could lose their kids. They don't stop identifying as a parent, because if you hear them talk, they say like, yeah, I'm the parent of a boy. I lost my boy 5 years ago, right? They don't say, oh, I'm not a parent. It's like, no, you are a parent. They identify as a parent. They just lost their kids, right? So it's something that really is a powerful identifier, and it's a strong commitment. You know, even if you just basically send your kids out to pasture and you don't have anything to do with them, it's like you're still a parent. You may not be a very good one, but that's a different question, right? But you're still a parent, and so that's part of your identity. Now, for those of us who don't like kids, right? It's like, yeah, no, me and kids, like oil and water, I'd rather spontaneously combust than have kids. I can't really be around kids without strangling them. So that's usually frowned on. Most people don't like you strangling their kids. That's usually a negative thing. You can go to jail for that one. Right. So for you, it's like, yeah, no, it's like a big no. I'm not going to have kids at all. Well, that's fine. Right. Then you just got to go do you. You do your thing, right? Do your whatever, build your career, live your life, whatever you want to do, whatever that entails. And there's a lot of people who do that, right? Who just decide, listen, I don't want kids, I don't want family, I don't want any of this stuff. I just want to do my thing. I want to do my career, I want to live my life, and that's fine. That's like your G0 state. That's like your functional state. That's you being who you are and being what you are. It's like when you're talking about a cell, like a liver cell is a good example I like to use, because liver tissue has partial regenerative capacity, so they can divide a little bit, not much. But like a liver cell who's hitting the restriction point, they look around, they say, do I need to divide? And the answer is like, well, no, we're good, right? Liver's healthy, we don't need to divide, we don't need more cells. You just go do your thing. Then that cell just goes and does its liver thing. It does its metabolism, it just does the job of a liver cell. That's all it does. Now, can it come back and enter the cell division cycle? Sure. Right? Just like somebody who says, no, I just want my career, can later in life be like, you know what, I'm in my 30s now, I've made my money,
I'm feeling good about my career. I've been around the block a few times. I think I'm older now. I kind of see things differently. I want to have a kid, right? And you can. So, you know, you can come back and to it. Basically what's happening in G1. So let's imagine you commit to it. You say yes. At this point now, you have to follow your mantra. Duplicate, separate. So the first step is duplication of DNA. So you duplicate your DNA, and this is chapter 14, so we'll talk about the details of DNA replication later on. And then again, after this, you hit the next phase, which is G2. This is another pause in the cell cycle. And here, what's happening at G2 is you're replicating now and duplicating your organelles. You're making and organizing your microtubules, and you're getting things prepared for the actual separation. You're not separated yet, you're still duplicating, but you're getting things ready for separation. A couple of things you're also doing here is basically you're doing DNA repair. You made some mistakes during replication. It's okay, it happens. But now what's happening is you're going back to the repairing those mistakes so that everything is spot on perfect. Okay. Then once you finish with G2, together collectively, all three of these are referred to as interphase, the intervening area between two mitotic. Then after interphase, once you kind of clear all the checkdowns in G2, you're ready to roll, you're doing your final checklist and that sort of stuff, then you move on to mitosis, which is the division of the nucleus, which is subdivided in 5 phases. And we'll talk about those phases and what's happening in each of those phases later on. And then from there, you enter into cytokinesis, where you have the division of the cell, the cytoplasm. And then you create the 2 new daughter cells, which then they go back into E1. They go through their growth phase. So, last topic. A lot of questions, questions out. Well, how long does this last exactly? Depends, right? If you're a fruit fly embryo, you're moving pretty quickly. So 8 minutes. You're turning over in 8 minutes. That's pretty fast. Yeah, good. Correct. That's also part of it. Yeah. So in mammals, on average, you're taking 24. Different mammals will be 24 hours, that is, not 24 minutes, right? So different mammals will be different. Different cells within the same mammal will be different. Here's a good example. If I have a skin cell in my body, my skin is turning over roughly every 14-ish or so days, right? So that represents a high mitotic rate of replacement. Same thing for you guys. My liver, however, can take more than a year. So just within the same body, you can have dramatically different cell division rates. Most of your time is spent in interphase. You're preparing, and very little of it is spent in M phase. Why? Because remember, this is your cellular pants drop. When the time comes for you to drop your pants in public, are you going to be lingering in that state for a while? No, that's going to be the fastest thing you've ever done in your life, right? But when you get yourself up to that point, you're probably going to take your time, aren't you? You're going to be like, you know what? I want to do this. Ooh, I want to do this around. Like, some of these people look a little angry. I don't think I want to be vulnerable in the midst of a bunch of angry people. I'm going to come over here because these people look like they're fairly sympathetic and empathetic. So they might actually feel sorry for me. So I like this crowd over here. So notice I'm taking my time, organizing and getting myself prepared to really make sure that I'm ready. So that when I do the pants drop, it's fast and as non-damaging as possible, right? So we'll pick up with this slide next time.